All right, this short video is going to help introduce you to the concepts of beam stability. Okay, beam stability can be compromised in two different ways. What we call local stability of the cross section, such as the flanges in the web, and overall stability, which means the entire cross section becomes unstable. Okay, so we have local stability effects. Okay, and we have stability, and maybe what we can refer to as global or overall stability. Okay, and then the global or overall stability can be accomplished by having flange bracing and torsional bracing, I should say, or torsional bracing. Torsional bracing. Okay, so that's what we'll review here quickly. All right, so if a beam can remain stable, and again, stable means local stability, locally, right? So the flanges, remain stable in the web, and globally. All right, we'll see that it's possible for this beam to kind of rotate out of plane. It goes through a twist, okay, and it goes through a lateral displacement. Okay, so if we can provide a beam that's stable in both conditions, it can reach full plastic moment capacity. And again, M sub P is going to be Zx times Fy, or whichever axis it's bending about, Zx or Zy. If we cannot assure stability, either locally or globally, then the nominal moment will be less than the plastic moment capacity. Okay. So we want, ideally, the beam to reach full moment capacity, full plastic moment capacity, where the entire portion of the beam that's in compression reaches F sub Y, the entire portion of the beam that's in tension reaches F sub Y also. Okay, and again, there's two conditions that we must meet. Okay, this lateral torsional buckling, which would be what we refer to as global buckling, okay, and then local instability, which is a function of the B over T ratios, similar to what you did for columns. Okay, so this would be a local element stability. So overall, the entire cross section could go from being straight to rotating out of plane, okay, and displacing laterally. Okay, so that's a global. And then the local is when the web buckles or the flange buckles. Okay, and I do have, I guess I got that in the way there. There is a video on lateral torsional buckling and local buckling. The lateral torsional buckling video walkthrough is in this section, 5.3, and the local buckling walkthrough video is in section 5.4. So make sure you check those out. So lateral torsional buckling, which is the global effect, right? This is the global effect, and that's when the beam will rotate out of plane due to loading. Okay, we always assume at the supports it is braced so that no twisting or lateral displacement occurs. The longer the unbraced length, right, this is what we're going to refer to as L sub B. The longer the unbraced length, the weaker the beam will be, just like columns. The longer the column was unbraced, the weaker the column was. So we can also add additional bracing, right? We could brace it to concentrated loads and change the unbraced length and therefore increase the capacity of the beam. We could attach metal deck to the top flange, to the compression flange, and that will change the bracing conditions. But that bracing does two things, right? It prevents lateral movement, right? So there's my DX, so to speak, a lateral displacement to the left. And this type of bracing is referred to as lateral bracing. So it prevents this flange from moving left to right. Then there's what we refer to as torsional bracing. And torsional bracing prevents the entire cross section from rotating. So torsional bracing prevents this. Okay. So somehow we have to establish that the beam will not twist and the beam will not laterally displace at what we're calling a bracing location. Okay. Then once we provide global stability, right, we could have, local instabilities. It's possible. Local instability. It's possible that the flange or the web could buckle before we reach full moment capacity. So this, buckle here in the web or a buckle here in the flange. The flange is more obvious, right? So it's failed locally. That's what we would call as a local flange buckle, flange local buckling, or web local buckling. Okay. Web local buckling is more of a plate girder problem. You got to be careful for plate girders. Rarely does it control for rolled sections, wide flange sections. Flange local buckling, you got to be concerned with all the time. Okay. And we will see this occurs in some wide flange shapes in our steel manual. Okay. But the good thing is it's very few. Okay. So again, compression element, just like in the column, you have to classify them as compact, non-compact, or slender. Okay. And if you look at user note F2, right, here, right, it'll tell you that very few flanges are non-compact and all webs are compact. Okay, so it's not as big a problem as we might think. It just occurs every once in a while. It's just something you have to make sure you remember to check. Okay, so we want to avoid flange local buckling and we want to avoid web local buckling. Again, not very common. Or I shouldn't say, I'd say this is not very common. I'd say for wide flange shapes, not a problem for wide flange shapes. For standard wide flange shapes, right? For rolled, I should say, rolled W shapes. Okay. And it is a function of with the thickness ratios. Okay, so we'll see that in the next section, 5.4. All right, but rest assured, it's not as something that happens very often at all. All current shapes have compact webs. The only shapes that do not have compact flanges are listed here. Again, for FY50, which is probably the most common yield stress that we use. Okay. So hopefully that's helpful. Again, we'll get more detail in section 5.4 and 5.5.